At the heart of our most fundamental theories, from Newton's mechanics to Einstein's relativity and even the strange rules of quantum physics, lies a disturbing symmetry. These laws work perfectly whether time runs forwards or backwards. A video of planets orbiting a star or two particles colliding and flying apart would look just as physically plausible if you played it in reverse. Yet in our universe, teacups shatter but never reassemble themselves. Eggs fry but never unfry. We remember yesterday, but we have no memories of tomorrow. This glaring contradiction, this one-way street we call reality, isn't written into the basic code of the cosmos. It emerges from something far more profound, a law so absolute it has been said to hold the supreme position among the laws of nature, the Second Law of Thermodynamics. But physics whispers a far more profound and perhaps tragic truth. Our very perception of a past, a present, and a future is inextricably linked to the universe's ultimate demise. This isn't just philosophy, it's the ironclad grip of the second law. The law states that in any isolated system, a quantity called entropy can only increase or stay the same. It never decreases. Entropy, in its simplest sense, is a measure of disorder, randomness, or multiplicity. Imagine a brand new deck of cards, perfectly ordered by suit and number. This is a state of low entropy. There's only one specific way for it to be perfectly ordered. Now throw the cards in the air. When they land, they will be in a jumbled, disordered state. This is a high entropy state, not because disorder is some active force, but because there are astronomically more ways for the cards to be disordered than for them to be ordered. The universe, on a cosmic scale, is constantly shuffling its own deck. This isn't a suggestion, it's a statistical inevitability. The physicist Ludwig Boltzmann etched this concept into the bedrock of science with his equation, S equals K log W. In plain language, a system's entropy is directly related to the number of possible microscopic arrangements of its components that result in the same macroscopic state we observe. A shattered teacup has its molecules in one of a near infinite number of jumbled configurations. A whole teacup has its molecules locked in a very specific, limited set of arrangements. The universe is overwhelmingly more likely to move toward states with more arrangements, towards higher entropy. This statistical reality is the engine behind the arrow of time. The reason heat flows from your hot coffee into the cooler air and never the other way around is because the state where the energy is spread out evenly is vastly more probable. The energy isn't trying to disperse, it's just that the number of ways for it to be dispersed is gargantuan compared to the number of ways for it to remain concentrated in your cup. Every process, every interaction, from the light of a distant star reaching your eye to the chemical reactions powering your own thoughts, is a step in this universal march towards equilibrium. So, the arrow of time isn't a fundamental property of time itself. It is an emergent property of the entire universe, born from the fact that it began in a very special, highly ordered, low-entropy state. This is the great past hypothesis. For the arrow of time to exist, for us to be able to distinguish yesterday from today, we must assume that the universe, some 13.8 billion years ago, was wound up like a cosmic clock, in a state of improbable order. Every tick of that clock since has been the sound of it winding down, of its entropy increasing. Your past is nothing more than a record of the universe in a less disordered state. Every memory you hold is a fossil, an imprint of a lower entropy configuration that can never be perfectly revisited. The flow of time is the wake of this cosmic unraveling. But if this is true, if our entire reality is built upon this one-way journey from order to chaos, then what is this process creating along the way? What if this fundamental cosmic decay is the very engine of our reality, the prerequisite for consciousness itself? Building on that relentless march towards disorder, we find that entropy doesn't just dictate the flow of time, it fundamentally shapes our existence. The deep puzzle has always been the starting point. Why did the universe begin in such an incredibly low entropy state? At first glance, the Big Bang sounds like the opposite of order, a singularity of unimaginable heat and density. But this confuses thermal disorder with gravitational order. The key lies in gravity. For a system governed by gravity, a smooth, uniform distribution of matter is a state of profound, improbable entropy. The high entropy state is one where gravity has done its work, clumping everything together into massive, dense objects like black holes. The evidence for this pristine initial state is etched into the very fabric of the cosmos. It is the cosmic microwave background radiation, the faint afterglow of the Big Bang, captured in stunning detail by missions like NASA's WMAP and ESA's Planck satellite. This ancient light shows a universe that was almost perfectly uniform in temperature. A smooth cosmic fog with density fluctuations of only 1 part in 100,000. That smoothness, that gravitational order, was the universe's starting capital of low entropy. It was the potential energy that has fueled every single complex structure that has ever existed. From those minuscule ripples, the story of complexity unfolds. Gravity, acting over eons, pulled matter from the slightly denser regions into filaments, then clusters, then galaxies. Each star that ignited was a magnificent engine of entropy. It took highly ordered fuel, simple hydrogen and helium atoms, and, through nuclear fusion, forged them into more complex but ultimately less ordered heavier elements. In the process, it radiated immense quantities of high-entropy energy, a chaotic flood of photons, out into the cold void of space. Our sun, in its brilliance, is massively increasing the universe's total disorder, and in doing so, it carves out a small temporary pocket of conditions suitable for life. Life itself is the ultimate local rebellion against entropy. An organism, a tree, a human being, is a structure of breathtaking complexity and order. This doesn't violate the second law, because life pays a steep entropic tax. To build and maintain our low-entropy bodies, we consume ordered energy and export a far greater amount of entropy back into the environment in the form of waste heat and disordered molecules. We are intricate eddies of order in a vast cosmic river flowing towards chaos. And nowhere is this bargain more profound than in our own minds. A memory is not an abstract concept, it is a physical structure. It is a specific, highly ordered pattern of synaptic connections within the neural network of your brain. To form a single memory, to encode the face of a loved one or the words on this screen, your brain must consume energy, burn calories, and release heat, meticulously arranging neurons in a configuration that has an infinitely small probability of occurring by chance. You are literally paying for your past with the universe's future. Your ability to distinguish before from after is entirely dependent on this process. We have records of the past, memories, fossils, craters on the moon, because the past was a lower entropy state from which these ordered imprints could be made. We have no records of the future because it is an unwritten high-entropy wilderness of statistical probabilities. This leads us to the ultimate inescapable consequence. What happens when the cosmic clock finally winds down? The universe's heat death. In the unimaginably distant future, all stars will have burned out. All matter will have decayed or been swallowed by black holes, which themselves will have evaporated over trillions of years through Hawking radiation. The cosmos will become a vast, cold, and perfectly uniform soup of elementary particles. This is the state of maximum entropy, thermodynamic equilibrium. In this final state, no work can be done, no complexity can form. And with no change possible, the arrow of time dissolves. Past, present, and future will become indistinguishable, meaningless concepts. The tragic beauty is that our ability to perceive time, to create and remember, is a direct consequence of this cosmic process, a fleeting dance on the edge of universal oblivion. We exist only because the universe is on an irreversible journey towards a state where nothing, not even the memory of us, can possibly exist.